here telling us about how to untwist the pure spinor formalism. Who knows what to unravel into?
Okay, so thanks very much for the organizers for a nice workshop. So, I'll talk about this based on a paper a few months ago. I'll start by reviewing RNS, which of course has an n=1 worldsheet supersymmetry. And then I'll say, I'll give you a quick review of this pure spinor formalism that was already mentioned. It's not on? Pure spinor formalism, which was mentioned a few times, which has advantages when you want to compute multi-loop amplitudes because there's no sum over spin structures, and when you want to describe Ramond-Ramond backgrounds like ADS5 times S5, which people don't know how to do using the RNS formalism. So those are the advantages of pure spinor formalism, but there are some disadvantages. So the worldsheet structure is not so well understood, and furthermore, the relation to RNS, where the worldsheet structure is well understood, is mysterious. So it's been shown that the amplitudes coincide for all the amplitudes that were computed on both sides, but giving a direct proof without having to do the computations hasn't yet been done. So what I'll describe here is there's of course a way to get an n=1. So this pure spinor formalism has an n=2 worldsheet supersymmetry, which I'll say a little bit about. It's constructed from the B ghost together with the BRST current. So those are the two fermionic generators. And they, of course, close to give the stress tensor, and there's also a U1 current in that n=2, which is just a ghost number. And, of course, the n=2 has a subset, which is n=1, which is just by summing the B ghost with the BRST current. And that's what I'll discuss here. In order to, this is twisted naturally because the BRST current has conformal weight 1 and the B ghost has conformal weight 2. But you can untwist using the ghost current to make it, both the fermionic generators have conformal weight 3 halves. And then you can, of course, add them to get an n=1. And it's natural to conjecture that's related to this RNS. And I'll say some things about that. And in fact, you can describe this formalism in a way with manifest n=1 worldsheet supersymmetry, just as you can in RNS, at least in the Neveu-Schwarz sector, you can do this in RNS. So I'll show how to write, for example, the pure spinor action in terms of these n=1 worldsheet superfields. And now I'll discuss some applications, for example, how to formulate the vertex operators and at least compute tree amplitudes. So, of course, using the pure spinor formalism, it's been computed up to 3 loops. But at least using this n=1 worldsheet supersymmetry, I only know how to do tree amplitudes at the moment, but obviously it would be nice to try to generalize to the loops. And one thing you understand in a nicer way using this n=1 description, and I'll say something about, is the role of the B ghost. So in the pure spinor formalism, the vertex operators are normally not in what's called Siegel gauge, which means they're annihilated by the BRST operator, but they're not annihilated by the B ghost, as they are, for example, in Siegel gauge in bosonic strings. Whereas using this n=1 structure, it will be natural to understand exactly why. And in fact, you'll see how that comes in. And that may help in understanding loop amplitude. So one of the obstacles to going above 3 loops is essentially the role of the B ghost. So of course, it's going to be complicated to compute higher than 3 loops, but at least one should have a prescription. And at the moment, that's a little bit tricky because of the B ghost. Now, another advantage of this n=1 is it turns out to give a simpler version of the ADS5 times S5 action, which was written before in the pure spinor formalism. In this way, in this method, you can write it with n=1 worldsheet supersymmetry. So unlike in RNS, where you can only describe Neveu-Schwarz backgrounds using n=1 worldsheet supersymmetry, now you can also describe Ramond-Ramond background. And in fact, the action seems to be much simpler, and hopefully that can be used to do some computations in ADS5 times S5. Okay, so that's the motivation. So let me start by just reviewing the RNS. Are there any questions? So interrupt me whenever you want with questions. Okay, so just a quick review of RNS. So of course the action is constructed from so I'll discuss just type 2. So you have left moving psis and right moving psis. So these are the fermions. And if you want to make it manifestly worldsheet supersymmetric, you also introduce an auxiliary field. So all of these are vectors, of course. And they fit into a superfield. So I'll use kappa and kappa bar for my left and right moving Grassmann parameters on the worldsheet. And the auxiliary field sits just in the last component. And you can write this action if you want in manifestly worldsheet supersymmetric language by integrating out the kappa and kappa bar. So the action is just dx d bar x, where d is d kappa plus kappa dz, and d bar. So this, in addition to having the usual worldsheet superconformal worldsheet conformal invariance, it has, of course, an n equals 1 comma 1 worldsheet superconformal invariance. And of course, you can write down the stress tensor if you want. And I'm not going to discuss the ghosts. So in fact, what I'll describe here is essentially ghost-free. So I won't discuss central charges and things like that, but that can be fixed up in the end. Okay, now the usual amplitude prescription that people write in RNS is where you choose these vertex operators in different pictures. So the vertex operator for the gluon, you can write in the what's called the zero picture. As an integral over kappa of this object here. So dx is, of course, a superfield which starts with psi. So this starts out with psi m am, but when you do the integral over kappa, it turns this into a dx. So this is equal to, after doing the integration over kappa, is equal to dxm am plus psi m. Now one can construct scattering amplitudes using just these v's for tree amplitudes. If you want to do for loop amplitudes, it seems you need vertex operators in other pictures. But for tree amplitudes, there's a nice way to write the scattering amplitude, which is you do the correlation of n of these, but you fix 3 of them. So let's call the ones you fix z1, z2, and z3. And you can write, so we fix these at z1, z2, z3, and we integrate over all the others. So it looks precisely like the bosonic prescription, bosonic amplitude prescription, where in the bosonic prescription these would come from the C ghosts. But since I'm writing things without any ghosts, you can just use this prescription to get the tree amplitudes out. As I'll mention, it's not known how to generalize this to loop amplitude. At least I don't know. Okay, any questions up to now?
Those V's are the same, the fixed V's are the same form as the...
All the V's are the same form. Some are n minus 3 are integrated, and 3 are unintegrated. So it's precisely like in bosonic strings here. If you want to do gluon scattering in bosonic strings.
I mean, if I introduce ghosts to the fermionic system...
Don't think about it. This is the answer, okay? If you want to put in the ghosts, that's when I try to generalize this to loops, I'll get problems because of these ghosts. But a tree amplitude is just a prescription that gives the right answer. This was called, I don't remember if it was called F1 picture or F2 picture, but there was a picture called this when before people knew about ghosts. This was one way to go. Okay, so now let's do pure spinors. So the degrees of freedom are different. We have xm, so same x as before, but now we have theta alpha. So we're going to have space-time supersymmetry. In addition, you have to have a conjugate momentum to theta, which I'll call p. And these are left movers and right movers. Okay, so this is a set of... And finally, there's a set of objects which you can think of as ghosts. Although I won't tell you what gauge invariants they come from fixing. I'll just call them ghosts. Now I'm going to do type 2a and type 2b at the same time, which means that this alpha hat describes the right movers, and it's the same chirality as alpha if you're doing type 2b. It's the opposite chirality if you're doing type 2a. Okay, so the action in a flat background is very simple, which is why it's much more convenient than, for example, Green-Schwarz, where the action is not so simple, even in a flat background. So, of course, the bosonic part is similar. The fermionic part is first-order action. And the reason why it's called pure spinor formalism is because these ghosts are bosonic. So the space-time spinor is but bosonic, but they satisfy a constraint. So the constraint is that both the left and right movers are constrained to satisfy this. You can show that this constraint implies that lambda, instead of having 16 independent degrees of freedom, like a Majorana-Weil spinor in 10 dimensions, it only has 11 independent components. And you can show that if you Wick rotate to SO10, this manifold here has 10 complex degrees of freedom because it's a 20-dimensional real manifold. And if you, this would be a projective pure spinor, and if you include the scale factor, this has 11 independent complex components. Okay, so this is the pure spinor formalism. You can show that there's no conformal anomaly. But to describe physical states, you have to construct what's called a BRST operator. Now, I'll write the BRST operator. So first of all, you have the stress tensor, of course, which is so this is conformal weight 1, this is conformal weight 0. And similarly, this is conformal weight 1, this is conformal weight 0. So this would be the left moving stress tensor. And then you have a BRST operator, which I'll write in the form of a BRST current, which is defined to be lambda alpha d alpha. I have to tell you what d alpha is. D alpha is not the fundamental field, but it's constructed out of these fundamental fields in a manner which is space-time supersymmetric. So, of course, space-time supersymmetry acts on x and theta in the usual way. It shifts theta by a constant, shifts x by epsilon gamma theta, and it also has to shift p alpha. Now, as I mentioned before, there's a p ghost in this formalism, which satisfies the property that if you call this g plus and this g minus, like the two fermionic generators of n equals 2, the commutator gives you the stress tensor. Okay, now the B ghost is a bit complicated. So it starts off like what you might think. It's something like W d theta. That's going to generate this kind of term. But in order to generate this term, you have to introduce a fixed pure spinor. So I'll call the fixed pure spinor lambda bar alpha, which has the opposite chirality from lambda alpha. Okay, so the term you have to add is of this form, and you have to divide by this lambda lambda bar in order that when you contract it with this lambda d, it gives you this dx dx. So this B ghost has two unpleasant features. One, it depends on this fixed spinor. The lambda bar is a fixed spinor. So that, of course, breaks manifest Lorentz invariance. And it also involves inverse powers of lambda. So these are the things that cause problems when you go to loop amplitudes. Now there's one more thing I should say, which is because of this lambda gamma lambda constraint, this object is not gauge invariant. W alpha doesn't commute with lambda gamma lambda. But you can add a term which makes it gauge invariant, which is of the form So when you do the gauge transformation of this, it cancels the gauge transformation of this. So the gauge transformation is delta W alpha equals for any capital lambda. Okay, so this is the B ghost, which satisfies G plus with G minus this T. And there's a U1 current which comes from the double pole of G plus with G minus, which is just W alpha lambda alpha. So that just comes from the contraction of this. Oh, I didn't tell you what pi m. Pi m is the space-time supersymmetric version of dx. So if you're doing Green-Schwarz, this of course is already in Green-Schwarz, and d alpha is what's called the fermionic Green-Schwarz constraint. Okay, this forms an n equals 2 algebra. It's crucial that lambda alpha is a pure spinor so that G plus has no OPE with itself. Okay, so that's those are the key aspects of the pure spinor formalism that I'll use. And yes?
You don't have to introduce a fixed spinor in that case, is that right?
No, so but it's not, I mean, all of these hybrid formalisms are related by a field redefinition to RNS. This one is not, it's just by hand. Okay.
That J just gives you the ghost number.
I'm sorry?
The J just gives you the ghost number.
That's right.
Yeah.
Sorry, what's the tensor structure of the last term in the B ghost, in the numerator?
W get, oh, you're right, there's missing a term, thank you. Lambda gamma m d theta. So essentially subtracting off the non-gauge invariant part of that.
Oh, okay, yeah.
Okay. Any other questions? Okay, so to compute scattering amplitudes from this, well, first you have to write down vertex operators. So instead of writing down, let me write the unintegrated vertex operator first, just because it's simpler. So for the gluon, it just has this form where A alpha is the superfield, which corresponds to the gauge field, the spinor gauge field of super Yang Mills. So A alpha and AM covariantize the usual so this would be the covariantization of the supersymmetric derivative. Now you can also write the integrated version of the vertex operator. It has a few more terms. Starts out with the same superfield as before, but it also involves derivatives acting on this. So here's the AM, the same AM is here. And then it starts to involve field strengths. So W alpha is the superfield which starts with the gluon. And there's one more term which is, this involves the ghosts, and it couples to the superfield whose lowest component is the field strength. So these are all in superspace. And if you want, you can use this same formula, plug it in here, and get the tree amplitude. That's not the way it was originally done in this pure spinor formalism, but you can do that, you can use that method if you want. One thing I already mentioned is it's easy to show that QV equals 0. So Q is equal to the integral of G plus.
That's right. If you just use the V's to get the tree amplitude, you don't need to use the lambda Q piece of the bit.
That's right.
Identity. It just,
That's right. You just use
the lambdas and the W's.
use it 1 is equal 1.
Yeah.
Okay, so Q is the integral of the BRST current, and this V is constructed such that QV equals 0. Well, more precisely, QV is equal to the derivative of U, which means that Q of the integral of V, ignoring surface terms, is 0. And furthermore, V is defined up to BRST trivial. So if you do a BRST trivial transformation on U, that just corresponds to a gauge transformation on A alpha. So this is the usual definition of physical states. In pure spinor formalism, it extends to massive states, but of course the massive vertex operators are more complicated. And of course for supergravity, you just have lambda and lambda hat. So for supergravity, U would be lambda alpha, lambda hat, alpha hat, A alpha, alpha hat, X theta, theta. And there's a similar formula for V. Okay, so that was a review of pure spinor formalism, at least the ingredients that I'll need. There's one more thing I should mention. This action here are written in terms of the x's and p's and thetas. If you want, you can write it directly in terms of the space-time supersymmetric variables. So it has the term -1/2 pi m pi bar m. But then there's another term, which is the B field, the same B that appears in Green-Schwarz. I'm not going to write it explicitly, but it's antisymmetric in Z and Z bar. And if you add these two terms, you can convert all the D's into the P's into D's. So now it's manifestly supersymmetric. Okay, that will be useful later.
Is that just in flat states, or is that any target?
In any target. So in any target, of course, these pi's now involve the super Vierbein, and this B becomes also the full curve super Vier. And these D bars become connections, so you have to covariantize them, but it does generalize in curve background. Since you brought it up, if you introduce a Ramond-Ramond background, there's an additional term you add, which is not in Green-Schwarz, which is the Ramond-Ramond field strength, we'll call F alpha alpha hat times G alpha. So this is a coupling which you need if you're doing Ramond-Ramond background, which doesn't exist in a flat background. Okay, any other questions? Okay, so now I want to go to this new stuff, which is...
Sorry, what was the capital B there again? Sorry.
Okay, so capital B in Green-Schwarz, it's antisymmetric in Z and Z bar, and it has terms of this type. So I'm not going to get the coefficients right. So it's antisymmetric in Z and Z bar, and it has this type of coupling. It has the property that D of B is something simple. So H is simple, but B, at least in a flat background, has this form. This is the same as in Green-Schwarz. Okay, any other questions? Okay, so now we want to define untwisting. So we have the n equals 2 generators. I told you what untwisting means. Untwisting just means shifting the conformal waves. Green is probably not a good color. So I'm going to add a term to T, which is a derivative of J, with a factor of half, and I guess probably minus. So
Before you say that, could you say what the value of the central charge is for the n equals 3 alpha?
I didn't include the quantum corrections. So I'm not going to, I'll try to give you the answer later in a careful way, but without including the quantum corrections, I can't tell you. Okay? This gets quantum corrections also because you can add terms like, once you include lambda bar, you can add terms like lambda bar d lambda, these kinds of terms which change the central charge. Okay, so we want to untwist it. So I add this term to T, I've untwisted it. Okay? But now we want to make the n equals 1, so now there's a subgroup, which is, I'll call G, equal G plus G minus, I'm not going to rewrite it because there's g plus and g minus. It's just stupid. And that, of course, satisfies the usual algebra with now the untwisted t. So let me call the untwisted t. T tilde. So g with g goes to now t tilde over 1 minus t. And now we want to build n equals 1 superfield. So we're looking for n equals 1 superconformal primaries. So we just have to look for objects which transform covariantly under the n equals 1 superconformal transformation. And that's not so difficult. You start with x, and you just ask how does it transform under g plus and g minus. So we just have to pick out all the poles of x with g plus and g minus, and that will tell us what these psi's and psi bars are. So we're going to have the same type of superfields as before, but now the psi and psi, or psi hats, will not be independent of x and theta. They're just going to come from the poles of x with g plus and g minus. So x with g plus is easy, just comes from the pole of x with this dx here. So you get the term 1/2 lambda again and theta. But you also get a contribution from x with g minus, because d has x dependence and pi has x dependence. So you get two terms. You get the term this comes from the pole of x with d, and then you get another term coming from the pole of x with pi. So the other term is so this is going to be the definition of psi, and there's a similar definition for psi hats. So they're not independent of the x of the thetas. You can similarly construct a superfield theta. Because it's left moving, you only have kappa dependence. In other words, g bar plus on theta would be 0 because theta is left moving. But g plus is not 0. You get it from lambda alpha, obviously, from g plus. So let me call this subject capital lambda alpha. And we'll find that capital lambda alpha is equal to small lambda alpha coming from here. And then there's a contribution from here. So it's going to be plus pi m now if you're clever, you can see that these two terms combine into just being 1/2 lambda gamma m theta plus or minus. Okay. So psi m is a mixture of thetas and its conjugate, which it has to be because psi with psi has a singular OPE. Now this capital lambda, remember, small lambda was a pure spinor. Capital lambda is unconstrained because it's easy to see that this has 11 independent components, but for fixed lambda bar, this has 5 independent components. So these two terms together fill out an unconstrained spinor. So if you want, you can either think of lambda and x as being your independent variables, or as we'll see later in other choices, thinking of these as being your independent variables. So in that case, you have an unconstrained spinor worth of variables.
Sorry, you probably said this already. After the twisting, lambda now has conformal weight 1/2?
Yeah, I forgot to say it, so it's good you say it. You said it for me. So both lambda and w now have conformal weight 1/2. So for example, 1 over lambda lambda bar now has conformal weight minus 1/2, which is why this has conformal weight 1/2.
So lambda bar is still the same?
Lambda bar is a fixed object,
Yeah, okay.
so it's just a constant. Okay, this doesn't yet complete the story because we still have the conjugate momentum to theta and the w which hasn't appeared anywhere yet. So we need one more superfield to complete the story, which I'll call capital phi alpha, which is going to start out with W alpha, or more precisely, it starts out with the gauge invariant part of W alpha, which is W alpha minus the same object that I wrote down before. This object here. And then if you do the variation of it, you find that it only gets a contribution from G plus, and it just gives you D alpha. But you have to subtract off this term because both of these contribute to give you a D alpha. Okay, so these are my three superfields, which essentially encode all the information I had before, but it does it repeatedly. What I'm trying to say is that these are related to each other. In other words, theta appears here in psi, but it also appears here. So obviously these superfields are related, and the relation is not very complicated to figure out. It's lambda bar alpha, gamma m, so if you take these superfields x and theta, and you compute this object here, which is space-time supersymmetric, for the same reason as small pi m was space-time supersymmetric, this thing is space-time supersymmetric, this object is identically 0. So that comes, it's easy to check, you just use the property of psi being written in terms of theta. The other constraint is on this phi, and that just comes from the fact that you're subtracting off this piece here. So it's easy to show that lambda bar gamma m phi equals 0. So these are the two constraints. Unfortunately, they're not Lorentz covariant. They explicitly involve lambda bar. By using these variables, these superfields, and these constraints, now we can do everything with manifest n equals 1 worldsheet supersymmetry. Okay, so the first thing we want to do is just write down the action. So up to these constraints, the action can now be written in the same form as we did for RNS. So it has a kinetic term for the fermions, which is the type minus phi alpha. So of course, there are left and right moving versions of theta and phi. And this just tells you that this one is left moving and this one's right moving. And you have a supersymmetric or worldsheet supersymmetric version of this action here. This one here. I guess it's a minus. Where this object here, I'm defining to be pi kappa. So this is the object, if you take a worldsheet derivative on it, if you look at its bosonic components, you get the ordinary pi. But it starts out as something fermionic. That's what this kappa means here. And finally, you need to add a b term, which is the analog of this. Essentially, you just replace these ddz bars and ddz with just the worldsheet, capital D bars and capital Ds. Okay. B, I got B tilde, just D bar. Okay. So after imposing these constraints, these two constraints here, you can show that this action reduces to the pure spinor action. Okay, so that's essentially the starting point. So that's, now we want to do something with this. But that's essentially the untwisted pure spinor form. Any questions? Yes, Kyle?
If you don't impose this constraint with lambda bar, do you have
Yes.
some sort of additional symmetry such that you can view that as fixing something?
So you can view some of that side. You can think of these as being constraints imposed with the Lagrange multiplier, and they are first-class constraints. So you can think of them as symmetries. That's right. Now, they're not Lorentz invariant symmetries, but okay, yes.
So then the lambda bar becomes a kind of a gauge fixing parameter.
No, I think, so the Lagrange multiplier, so the term in the action you would add is something like this times, so this would be the term you would add, where if you vary L alpha, you get this constraint, and the gauge symmetry would be generated by this. So I don't think you can think of this as a gauge fixing parameter, it's just part of the game, just fixes a direction.
Can't you have a non-minimal version of that?
Okay, so there are various generalizations of this that we can discuss at the end. I haven't been able to, but that doesn't mean, I haven't tried very hard, and it would be interesting to do it. But at the moment, let's just see what we can do with this. Now, one thing you can do with it is look for other solutions of the constraint. So that's, in fact, one way to solve the constraint is to eliminate psi and lambda alpha in terms of theta alpha and small lambda alpha. And then you get to the pure spinor form. Now doing that necessarily breaks the manifest n equals 1 worldsheet supersymmetry, because I'm choosing to solve for some of the components of a superfield and not for other components. But there are other ways to solve. So one thing you might want to do is try to relate it to RNS. Now this constraint here, there's nothing like this in RNS, because dx is supposed to be independent of all the other fields. But what you can do is, instead of solving for psi and lambda, capital lambda, you can solve for lambda gamma m theta and lambda alpha. In terms of psi m. I'll tell you what theta prime is in a second. So theta prime is a field which satisfies So what we've done is we've taken 5 of the 16 components of theta and we've written them in terms of size. And similarly, the conjugate momentum. So you have 5 of these, and the conjugate momentum gets written in terms of 10 size. And you're left with the theta, and let's call it p prime. Which are now constrained because they only have 11 independent degrees of freedom. That means they satisfy a constraint like this. Now in this description, we're left with x's and psi's. So the resulting fields are xm, as we had before. Now we have a constrained superfield, theta prime. And we still have phi alpha. So this is something like W. Now, you can try to write the action in terms of these fields, and you'll find that the action looks very much like the RNS, but there's an extra sector. So S is now equal to now the term is phi alpha e bar theta prime alpha. And these no longer talk to these. So you've solved the constraint, at least this constraint here. You still have this constraint here. So these describe just 11 independent thetas and their conjugate momentum. And it might be able to show that these decouple. If you could show that these elements decouple, you're left with RNS. Okay, now, at least for the massless vertex operators, I was able to show in the Nivert-Schwarz sector that they decouple.
So by decouple, you mean there's no dependence on those in any BRST closed vertex?
That's right. That any dependence on it is BRST trivial. So this I call extended RNS. So it's not quite RNS because it has this extra sector. And I certainly don't understand the Ramond sector yet. But this is certainly a step in the direction of showing how to relate to RNS.
What's the central charge of that extra sector?
Again, so the central charge of this, of course, is the usual part. This part, again, it can be adjusted. So I haven't been careful. I mean, I haven't worried yet about central charge contributions because there are extra terms you can add here with fix-up central charges. So I can't answer your question.
But in particular, you can choose it to be 0 by adjusting it?
I think so. I mean, I don't want to say yes. I've only looked at tree amplitudes where the central charge hasn't come in yet. But certainly, this is something that needs to be looked at.
I mean, naively, those are just free spin 1/2.
Yep, that's right. You have an equal, yeah, that's right. You have bosons and fermions, but I didn't tell you about, I haven't worried about it yet, so I can't tell you if it's going to work or not, but for tree amplitudes, everything works. Okay, now there's one other way to solve the constraints, which is interesting to this crowd and interesting to me also, because it's related to a previous description of Green-Schwarz, in which you use twistorial variables. So this is something, twistors used to be a bad word in the string theory community. Now maybe string theory is a bad word in the twistor community, so people call this embeddings instead of calling twistors. The idea is that instead of using the variables to solve for capital lambda in terms of small lambda, you can think of capital lambda as being the independent variable, and you're going to use it to solve for x in terms of capital lambda. So the idea is to solve for, use constraints, to solve for x, m, and psi m in terms of theta alpha and capital lambda. And then you also have the conjugate mental, of course. So what that does is it just eliminates the X superfield and just leaves you with now unconstrained superfields, which I'll call, so you still have the theta, but now this is unconstrained. And you have phi alpha, which will also be unconstrained, so I'll call it phi prime. And it will be related to the original phi by a shift. So I'll call this phi minus. So if you expand it in components, it has this form, where omega alpha starts out as before, like W alpha, but then there's an additional piece, W alpha minus this piece here. But then there's an additional contribution from here, which starts out as just. Now, twistor people will recognize this as the partner of lambda, which together with lambda form an SO10,2 spinor. So under SO10, 2 conformal transformations, this thing will rotate into lambda and vice versa. So by doing this shift, you do two things. First of all, you turn phi, or at least part of phi, into a twistorial superfield. And you also eliminate this constraint. So lambda bar gamma phi is no longer 0 because you've done this shift. So what we've done by doing this twistorial thing is express the action just in terms of thetas and phis without any x variables. So you can ask, what's the action? So in the flat background, the action is again, this is the same as before. But now there's an interaction term, which comes from the fact that the x's are now hidden in terms, hidden inside the thetas and phis. So you get an interaction term which is quartic in theta, which is of the type. So this last term is going to reproduce this term here. And you use this relation between the twistorial variables. Okay, so it's nice in the sense that it's not a very complicated action. It's not free, so it's not quite as simple as the other action. You can easily show it's manifestly space-time supersymmetric. You just have to know how the thetas transform under space-time supersymmetry. And it will turn out to have a nice generalization to ADS 5 times S5. Okay, so this twistor stuff, it's not yet well understood in the sense that I don't yet know how to write down vertex operators, for example, and compute scattering amplitudes using this. So all I've done here is just blindly use the definitions of theta and phi and rewrite the action in terms of these superfields. But well, it's still tricky to figure out how to describe these vertex operators in terms of these twistor variables. Okay, so that's an open question, which maybe I'll say something about at the very end. Okay, but one thing I do know how to do is to compute tree amplitudes not using this twistor approach, but using this n equals 1 worldsheet supersymmetric approach. So let me say a little bit about that. Okay, I think I can erase this.
So
Yeah.
you can rewrite the BRST operator and all these other currents in terms of these fields theta and phi prime.
Yep, so they're all quadratic because the worldsheet supersymmetry transformations are manifest, which means that all the component fields just transform linearly under. So Q is just something which rotates theta into capital lambda, and well, it's not Q, it's Q plus B. So okay, that's something which I'll say something about not right now is, of course, the original formalism had both Q and B. With this one, it looks like it just has Q plus B. Okay, so it looks like you've lost some information. Because we just have G, we don't have any more G plus and G minus. But you can, of course, still remember that you had a J. So if we define J equals W alpha lambda alpha, then, of course, J with G, it decomposes into G plus minus G minus, because these have opposite U1 charge. So if you're given J, then together with G, you can recover what you call G plus and G minus. So the first thing you want to define vertex operators is define what you mean by physical states. So in the pure spinor formalism, the definition was, well, we want states in the cohomology of Q, and it has to have a fixed ghost number. Fixed ghost number would be a fixed charge J. Now you can ask if there are, in this language, of course, the natural definition of physical states is n equals 1 superconformal primaries. Well, that obviously doesn't give you the right answer, because n equals 1 superconformal primaries, you have all these extra fields. So remember, we have 32 bosons and 32 fermions, right? So after solving the constraints, we have the same number of degrees of freedom as in the pure spinor formalism. So there's 16 thetas and 16 p's. There are 10 x's and there are 22 lambdas and w's. So we have 32 bosons and 32 fermions. And if it was just n equals 1 superconformal primaries, all you could do is subtract off 2 from each side. Okay, because you have 2 fermionic generators and 2 bosonic generators. One fermionic generator, but it's first class, so it eliminates 2 degrees of freedom, and similarly, the bosonic generator eliminates 2 degrees of freedom. Whereas you want to get, of course, 8 plus 8. So the other degrees of freedom you have to introduce are 22 and 22, okay, to get the desired result of 8 bosons and 8 fermions. So just in requiring that the primary field, that the physical states are n equals 1 superconformal primaries, that will have way too many states. Okay? You need another condition. So let me tell you now what the other condition is. So the other condition is that when you expand the vertex operators according to their U1 charge, so vertex operators will not have fixed U1 charge. Remember, before they had fixed ghost number. Requiring fixed ghost number is too strong. Requiring that there are n equals 1 superconformal primaries and fixed ghost number essentially kills all the physical states. But you can require that they have only non-negative ghost number. So we're going to require that they start with V0, where this is the ghost number, and just have negative. They don't have any positive. And I'll explain later why this is physically relevant. So what does this mean? So they have to be n equals 1 superconformal primaries. And they have to start out with V0 and then have negative ghost charge. So n equals 1 superconformal primaries implies that GV equals 0. As before in RNS. But because V has terms of different ghost number, this is going to imply that G plus of V0 equals 0. And implies that G minus of V0 is not 0, it's G plus of V minus 1, etc. Now remember, I told you one of the confusing points of pure spinor formalism was the B ghost did not annihilate the vertex operator. Now we understand why. It doesn't annihilate it, but it gives you Q of something else. Okay, so G plus, remember, is the BRST current. So this is the general form of the physical vertex operators. They have to be n equals 1 superconformal primaries, and they have to have ghost number either 0 or negative. Actually, this should have been minus 2. And in fact, this starts at minus. Because obviously this lowers by 1, this raises by 1. There's one other condition that we will need, which is that V0 has to be independent of lambda bar. So it will turn out that when we compute tree amplitudes, the only contribution will come from V0. And the vertex operators should be independent of lambda bar, just like this vertex operator is independent of lambda bar.
And G plus and G minus have different ghost numbers.
Yes, because they have different U1 charge. Okay, so now let me give in some examples, or at least one example, the massless vertex operator. So you might think that the massless vertex operator would just be d kappa of d theta alpha a alpha. This d theta alpha a alpha would be the analog of this thing I called lambda alpha a alpha, because d theta alpha is just, it's actually capital lambda. But so this is, of course, n equals 1 superconformal primary, but it doesn't satisfy these conditions here. To have it satisfy all the conditions, you need to add these terms. So this is the same AM as appeared here. And you need to assume phi alpha. So this vertex operator, like this one, is n equals 1 superconformal primary. And if you want, you can do the integration over kappa. And it contains precisely this term here. So let's call this V0. So now it's V0. But it contains other terms also. And you can easily show that these are in V minus 2. Okay, there's no terms of V minus 4. So the vertex operator has the term you wanted, but it has an additional term. And of course, B of V0 is going to give you Q of V minus 2. Now when we compute scattering amplitudes, we're going to use the same prescription as here, with the normalization that 1 is 1. What that means is that the only terms which will contribute in the amplitude are these V0s. Why? Because none of the vertex operators have terms of positive U1 charge. And because you need total 0 U1 charge to get something non-vanishing, the only contribution to this amplitude is the contribution where only the 0 component of all of these contribute. Okay? And that's of course going to reproduce the answer we want, because we already showed that in the pure spinor formalism this gives the right answer. Now for loops, other things can happen, and I'm not, perhaps, probably, these play an important role in the loops, which, okay, I don't have anything useful to say, so I won't say anything. But one thing you can ask is, for which vertex operators does this vanish? Okay, so there's some special vertex operators where this vanishes. And it turns out that V minus 2 is 0 if the vertex operator satisfies lambda bar alpha W alpha equals 0, if and only. Now, if you expand this in theta, what it means that the field strength, Fmn, is also 0, which means that when you look at the holonomy preserves lambda bar. So lambda bar is a killing spinor. So in backgrounds in which lambda bar stays a killing spinor, it turns out V0 is the only contribution, which if you go back one step, you can see that implies that J is actually a conserved current in that background. So in the backgrounds in which lambda bar is a killing spinor, you actually have n equals 2 worldsheet superconformal invariants, which is not surprising because this is related to Cobb-Bial manifold. Okay, so there's special backgrounds in which you have the full n equals 2, but in general you only have an n equals 1 subgroup. Okay, so let me just finish by telling you what the generalization of this is in ADS5, but without explaining it because I don't have time. So the generalization to that in ADS5 is you add a term to the action which includes the Ramond-Ramond field strength. So I told you here what term you have to add. I guess I erased it. There's a term of the type FDG, which in this language is F phi phi. And then you can integrate out phi from this expression, and you find that the action is you integrate out phi, you get an action just in terms of the thetas, and the action is very simple. It's where these thetas and theta bars are just written in terms of SU4 times SU2 comma 2. So the isometries of ADS5 times S5 are not SO91. They're SO42 times SO6, and these transform linearly under that transformation. So again, it's a quartic action. It's a different quartic action, but the fact that it looks not more complicated than a flat background makes you hopeful that you can do something useful with it. Okay, so I'll stop there.
Can you write the vertex operators for the ADS5 background?
There's one thing I didn't say, which is this ADS5 background was written in terms of the twisters. So this doesn't have the X's in it. And I don't even know in a flat background how to do it yet. But if I could do it in a flat, I suspect I could do it in ADS.
So does that look like an integral sigma model?
Yes, it is an integrable sigma model. So you can write this as a PSU 224 coset where you divide by the whole bosonic group. So this just gives you a fermionic elements, and theta is the lowest component of that superfield. And this is any symmetric coset of PSU 224. I don't know exactly what integrable means, but you can construct lax pairs for this, if that's what you mean by integrable.
Yeah, that's
and that you can do.
Yeah,
Okay.
That's good enough for me.
But this constraint, should I think of it as some sort of conventional constraint? I mean, why would you relate different solutions might
This one?
describe completely different theories?
So, yeah, so you can think of these different solutions as being different gauge fixings of that constraint in the line that Kelly was thinking of. But, I mean, it's just saying if somebody gives you a constraint, you can either solve the constraint by writing x's in terms of thetas, or you can write in terms of thetas in terms of x's, or... So, I think it's related to different gauge choices if you want to think of it in that language.
So where does immersion supersymmetry fit into these ideas? I mean, you've had the pieces in from the beginning here, whereas a year or so ago you were saying that you could derive the pieces from agents and
So
constraints.
connecting that to... So there was an earlier paper that he's referring to where I tried to understand Q as coming from a gauge fixing an action without any fermionic variable. So this action is already gauge fixed. So I'm not trying to derive this from some... I'm not trying to derive G plus from gauge fixing some earlier version. So in principle, the two could be related, but at the moment, they're just two distinct. They both involve twisters, which
Well, I know,
is clear.
I thought it would be a better way to get to the twisters to do the other one, but I mean, this looks fine too.
Yeah, you might be right. I mean, maybe this... Okay. Anyways, there are a million ways you could come from it.
Yeah. So if there are no more questions, let's thank Nathan again. Maybe